So the next speaker for today is our good friend, also our advisory board member, Govinda. So please come over here. So Govinda, he is going to speak on us actionable insights from bridge monitoring. So thank you so much.
Thank you, Tommy. Again, good to be here. Again, it's like coming to ANSHM forums. It's like coming back home and get to see all the familiar faces and the work that we're doing together to really try and advance not only the knowledge of this techniques and technologies, but also like collaboration with the industry and then pushing it forward. I'll just start with some of the challenges, and most of you are already aware of this. Most of our bridges in Australia are very old. Many of them are designed for 33-ton vehicles. They're still there, they're still standing, but there's a lot of demand now from like oversized, overmass vehicle that Desiree mentioned, with a lot of renewable projects happening. From things got to be moved from the port to the site, and the bridges are not very strong. And some bridges you see some defects, some issues there. But the approach that we generally use is we use traditional methods, very simplistic methods to analyze those structures, and oftentimes we see load rating assessment saying that load rating factor is 0.2, 0.3. Even the last one we saw like is 0.08, and this bridge is still there, still standing there, no visible signs of distress. But where's the cliff? So, and that's the concern, and it's all about sort of helping try close that plausibility gap, as well as really balance productivity versus safety risks. So in asset management terms, they use this term called the bathtub curve. So the bathtub curve, when you look at the failure rates throughout the asset life cycle, at a very early stage, assets can fail. So that is what is called infant mortality failure. And most of those failures are due to design issues or construction issues and all that. And there's the image on your right, top right. That's the bridge that collapsed in Florida due to some design and construction issues. And generally, asset owners and have some protection, contractual protection through defect liability clauses and all that type of thing. But then once you go along the life of the asset, particularly bridges, they've got a very, very long service life, and nothing happens for a very long period of time. So, and when you think about techniques like structural health monitoring and all that, so generally the life of those devices and systems around sort of 5 to 10 years, if that. But the life of the structure is 100 years. So, and where do you get value from all the sorts of things? But then now with the old assets and with the constant demand for the use of oversized, overmass vehicles, so we're getting very closer to this this end of life wear out failures, and we don't know where the cliff is, and sometimes every now and then we see bridges getting collapsed. This is the one in Italy some years ago, and not every one of them we hear in the news. There are a lot of bridges they keep collapsing here and there. Like our journey started by sort of really trying to understand what is the industry best practice in managing those assets from the understanding of the of its structural capacity side of things. So, and we stumbled into this SAMCO guideline, which is Structural Assessment, Monitoring and Control sort of guideline from Europe. And that particular guideline has got 7 levels of assessment when it comes to the existing assets, and we try to map that one with Australian practice as well on the right hand side. It starts with level 0, which is purely sort of experience-based subjective assessment, sort of like what we call touching distance sort of inspections and all that. So in Australia, we do that one very well. So that's our level 1 and level 2 inspections, probably one of the best in the world. So the way we do it, our authorities do that. And then the level 1 is the direct assessment of serviceability values from measured load effects. So if you don't have drawings, if you don't have information of your old structures, then you can measure the load effect So that's why I've highlighted that, like color that one in green, because there's an element of monitoring in there. And then after that, you go to level 2, which is the assessment using simple model, and we do a lot of that over here. And that is our desktop assessment and load rating that we do. But generally in Australia, we tend to stop there. Like regardless of what outcome we get out of that, we tend to sort of make decision based off that. But more and more we have started doing level 3 assessment here. So that is going a bit deeper into it. So what we call higher tier assessments or level 3 investigations that requires data from test and monitoring, etc. And then level 4 and level 5 is more sort of Collins domain, so using the principles of structural reliability and probabilistic methods. And believe it or not, there are some lead users, including Queensland Rail for that example, started using very advanced probabilistic assessment methods because some of their assets are very old, and no way those assets would pass AS5100 assessment. So there's got to be a risk-based approach. So essentially, the purpose of this one is to understand what is the latent capacity of the assets, and measurement can provide critical insights. So then we went through the journey working very closely with a lot of universities. We started our journey with Tommy, working on an Enterprise Connect project, really sort of understanding the technology and all the different layers of the technologies, starting all the way from sensors, data acquisition, edge computing, comms, to now like more advanced cloud computing, cloud infrastructure, and the user interface. So that has been a very interesting journey. The reason we were forced to develop this one because there's not a lot of off-the-shelf products available in the market. So that transition sort of, made us turn more into like a tech company from a more sort of like engineering advisory company. So essentially, the way this works is this is an event-based system. So there's a start trigger and an end trigger, and there's a duration of an event. So when the system picks up the start trigger, so we've got a lead-in portion of the sample that the signal that we collect, and also after the end trigger, the lead out. So that constitutes the event. And we captured these events for load crossings, and also the another thing was the bridge way in motion. There's a lot of literature out there. A lot of universities have been working on this one for a very long period of time, but now with the sensor that vibrating wire sensor in particular, that's a really sensitive sensor, and that allows us to do a lot of really advanced stuff. Because the signal to noise ratio is fantastic with those sorts of things. So now if we can put sensors in strategic location within the asset, then we can sort of understand the axles coming on and off the bridge, and by understanding the speed and the axle coming on and off, and using the fundamental principle of influence lines, then we can sort of really sort of map that, and also from the overall bridge response, scale that one to calculate what the axle loads are, and we've implemented this one on a few projects right now. So the effectiveness is fantastic. So so we can consistently calculate or estimate the gross vehicle mass much within sort of 10%. Accuracy. And then finally, it's about the interactability of the data. So once you see the data, you've got to be able to sort of play around with it. And as Desiree mentioned, like, you don't know what you've got, so you've got to take a deep dive, and sometimes you stumble into things that you never sort of intended to expect from these sorts of things. And another interesting thing that we discovered as part of the process is around sort of dynamic amplification. So the reference dynamic load allowance in the code is around 40% of highway traffic, and is so variable. It depends on wearing surface, your expansion joints, and all those sorts of things. And in one of the bridges that we saw this effect on one side, there was next to nothing dynamic effect. But on the other side of the bridge, where the vehicle sort of had to cross the the joint before entering to the bridge, then we can see massive dynamic effects. Some of them had even up to like 80% dynamic amplification, particularly the vehicle carrying sort of payload as an equipment payload. Then as it crosses, it gets into the bridge through the joint, then the payload gets lifted and then sort of sort of just smashes the bridge like that. And also another one, particularly the railway bridges, steel bridges, the fatigue is another consideration. And sort of right now we are working with one of the sort of international clients, and they need to actually assess their bridges for fatigue. Any bridge more than 50 years old has got to be assessed for fatigue. So fatigue is a really major consideration for street structures, and now this can be done real time as well. So essentially, there are quite a few problems that we started this journey with now have been solved. So now bridge and traffic monitoring can automatically generate a lot of things that I described before, and the key insights have been used quite effectively in different applications. So what is the next frontier? So from my understanding and my experience, that there are a few next frontiers. So one is certainly around, the most of them are around integration. And the first one is, I think, ITS. There's a massive untapped information out there, sort of through just ITS network, and how we actually integrate those data, fuse those data, and use the information that we get from bridge monitoring into sort of actual traffic control. So the second one, I think, is with integration with GIS, and there's another opportunity there, and particularly like as Arash mentioned, like it's a very simplistic to actually look at bridge in isolation. It's about the whole network, and using sort of modern GIS techniques and even sort of surveying techniques and all that, we can really understand how bridges are performing as part of the network, and also how it's interacting with environmental effects like with flooding or wind and all that. And the third one, I think, is the integration with building information modeling. So there's a lot of BIM technologies out there, not only for new construction, but also as part of the condition assessment of things like photogrammetric models and all that type of thing, how we actually sort of bring those things together so that we can see the defects in the bridge together with what our sensors are telling us about the bridge performance. And obviously, there are sort of a lot of emerging techniques and technologies out there, with Gen AI, anomaly detection, and all those sorts of things, non-contact sensors, wireless sensing, as well as vehicle structure interaction using the vehicle data. So there's quite a lot of techniques and technologies out there, and I believe we've just started our journey together, not only from Rockfield's perspective, but as a community. We're just at the very early stage, and we got a long way to go. And Tommy and ANSHM, like your initiative for establishing another hub for 5-year program of a lot of research in this area is really gonna help sort of advance our knowledge and understanding and application of these techniques. Thank you very much.
Thank you, Govinda. So it's very interesting talk, and also for your information, my PhD is working on wave in motion and dynamic amplification 40 years ago. So you can see the problems always there. Since 40 years ago, we start working on that. So maybe at that time I'm too advanced. Okay, so because of time, we could have 2 questions. Any question, or you like to leave it to the panel discussion? Yes, Colin.
I can't resist on the dynamic amplification. I think very careful. A dynamic amplification factor measured from a single vehicle loading event is not a dynamic load allowance. We have to be very clear about this. A DLA is what's applied to a critical static loading event, which is a multiple truck event, which is the 2,000-year return period event. It's an allowance, it's a probabilistic allowance that needs to be given onto purely static loading, right? It is not related to any single vehicle event. And using the same terminology for both different concepts is a cause for confusion, because we see horrible results like this and it makes people jump up and down and say, oh my God, I need to multiply my extreme static loading by 1.8, which isn't true, right? So we have to be very, sorry, I'm spitballing here, but comment please. Did you observe a reduction in dynamic amplification factor as your static strain increases?
It's a good question. We haven't gone into the DLA yet. So this is only our observation on dynamic amplification. And there's a really good point. That's why we've sort of made it clear that it's not DLA. The DLA is only a reference number. But if you look at the right-hand side, that particular bridge, if we actually work out DLA will come out to be very high, because consistently we're seeing very high dynamic effects on that particular thing, on the bridge number 2. But we haven't done the probabilistic assessment to see, like, this is the DLA that we got to use for this bridge. So, and it was a very good point, because people sort of use interchangeably the DLA and dynamic amplification, but that's not true. That's not right. Correct.
Thanks, Govinda. Just as an old man, I always like to go back to history. At that time when I work at PhD, we call it impact factor, and I introduced the name DLA. And now people use it, DLA. Okay, so last question.
Govinda, my question is basically, when we talk about the strain, and the previous presentation was a strain, so when we don't have a reference data, what's your thoughts on having a reference-free qualitative analysis rather than quantitative analysis? Is like, do you think qualitative analysis give us more confidence, or quantitative analysis on the data? A comparison, what I'm trying to say, when we do a bridge monitoring, so we can have qualitative and we can have quantitative. So this is very difficult to identify the status of the structure when we are going to start monitoring, which we don't have a history of a structure, right? And when we look at the linear analysis, and the previous presentation was basically also a strain analysis, which we are assuming the structure is following Bernoulli rules, and assuming the structure is still acting linear, and comparing these data. So I would appreciate your thought on that.
Oh, that's a really good question, Aris, and that's why, like, I think we got to be a little bit careful with just using. I don't call it structural health monitoring. I just call it bridge instrumentation and bridge monitoring as the only tool to assess the performance of the structure. It is a part of a bigger mix. You know, there's no substitute for fundamental engineering and really understanding the how the bridge performs, whether through simple assessment like Desiree mentioned, or using more advanced final element modeling techniques and all that. So we still got to use that to inform what the theoretical stress states and performance is, and then use instrumentation more as a tool to validate that and really understand sort of how the performance of bridge is. Not as a standalone sort of only tool that gives you everything. Did I answer your question? Yep.
Yes, Govinda, you did very well, just within short time to give a very good answer. Okay, thanks, Govinda. So we just